Hi everyone, this is Kumara, and in this talk I will introduce object-centric diffusion for efficient video editing. To start off, let's first look at the landscape of diffusion-based video editing. We can categorize the editing tasks into two categories, either style editing that focus on global changes, or shape and attribute editing that focus on local changes. In both these type of tasks, preserving temporal consistency is important, yet expensive. People rely on different techniques to preserve consistency, such as heavy cross-frame interactions, additional control signals, or correlated noise latents. So in this work, we try to address costs associated with these techniques. We first try to benchmark efficiency bottlenecks of these pipelines. We identify two types of bottlenecks, either corresponding to memory access or corresponding to computations. Based on these data points, we make a few observations on latency. First, one is obvious, that the latency grows with diffusion steps and with heavy attention. What's more surprising is that the overall cost is dominated by memory access, which you can see looking at the y-axis. Among computations, the cost is dominated by attention. And based on these observations, we make a decision that most of the latency is associated with the number of tokens. And if we reduce the number of tokens, we can directly or indirectly address both these type of bottlenecks. So why object-centric diffusion? If you look at shape or attribute editing, they specifically focus on editing only a localized region, for instance, foreground objects. Even in style editing, users mostly focus on salient regions, which means any artifacts in non-salient regions might not be that prominent. So we ask the question whether we can save the latency spent on background without compromising quality. To do so, we introduce two contributions called object-centric sampling and object-centric 3D token merging. So the idea behind object-centric sampling is simple. We want to sample background with fewer steps. To do so, we need to split foreground and background latents, sample them separately at different sampling rates, and at some point we need to merge and sample them together to avoid any boundary artifacts. If you look at the overall algorithm, we assume that we have access to a saliency mask which identifies foreground and background latents. If so, we split foreground and background and we sample foreground with the usual sampling duration given by delta t, whereas we sample the background with a higher sampling duration given by psi times delta t. At some point in denoising, we fuse these representations, and for the rest of the steps, we sample them together. By doing so, we avoid any boundary artifacts and any distribution mismatch. In object-centric 3D token merging, we first extend 2D token merging into 3D by sacrificing temporal redundancy while preserving spatial structure. Next, we plan to preserve more tokens in foreground regions by merging more in background. Let's look at an example. Here on the top row, we show standard token merging, and with red and blue tokens, we show the tokens that get preserved after merging. And if you look at the bottom row, in object-centric token merging, more of the blue tokens are constrained or localized on foreground regions or edit regions, and by doing so, we preserve the edit quality. And if we look at some qualitative comparisons, compared to our baseline fade 0, we see 10 to 20 times speed up. And even compared to other baselines, we are much more efficient. And finally, if we look at some limitations, object-centric diffusion still relies on per sequence hyperparameter tuning, which is expected in an interactive editing application. And we also observe that the most savings come at smaller object sizes. Please drop by our poster in poster session 4 for more discussions. Thank you.